Thank you. Yeah, sure. First, I would like to thank the organizers for having me here, for not being able to attend the first 3 days of the workshop. So IQ asked me to give a colloquium style talk. I'm not sure I can really do that. Certainly, there won't be anything new. So I just want to raise some recent development in sense theory. Just advertise some problems. So I find very interesting. So let me start with some classical work of Sen. So throughout this talk, so P will be a prime number, and so in his work on the divisible group, so Tate discovered the Hodge-Tate decomposition for Tate modules of William varieties. So I'm just stating a very restrictive form. So say A is a William variety over QP. So CP will denote the usual p-adic complex numbers or completion of algebraic closure of QP, and the absolute Galois group of QP acts continuously on it. So let's say show that there's a Hodge-Tate decomposition. Which says that if you take, I will use the homology, we talk homology instead of Tate module, just due to each other. If you take the atomic homology, first the atomic homology, and tensor is CP, then there is a natural decomposition. CP, for some with one, the global section of one form. CP, there's some twist here. And you should regard this as CP as CP0, and this zero, number 0 and the -1 up to a sign, or what people call Hodge-Tate weights. And this decomposition is it's natural in the sense that it commutes with all the symmetries you have here. So A is defined over QP, so there's the Galois group acts on it, and it also acts on CP. It acts on CP. So this is a Galois equivariance. And both sides are CP linear spaces, so actually this decomposition is also CP linear. And what Sen showed is that actually you don't have to start with a topomology of algebraic variety. You just need to start with a p-adic Galois representation, and after tensoring with CP, there is a natural decomposition. So in some sense, you can forget about the geometry and just study p-adic Galois representation, which is nice for me. So you generalize this to arbitrary p-adic Galois representation. By the way, I mean, you don't have to assume everything's over QP. You can just replace QP by a finite extension. But just for simplicity, let me just restrict in this talk, just restrict to QP. p-adic Galois representation. So in particular, so if you start with V, which is finite dimensional vector space over QP, n-dimensional for QP, and equipped with a continuous representation of the Galois group. So we'll then prove that so from this you can construct a natural element in the endomorphism of V tensor CP. We'll call Snell operator. So that's a CP linear and also commutes with the diagonal action of the Galois group. And so this Snell operator generalize this decomposition in the sense that this is spectral decomposition. So just in your linear algebra, so you will learn that for given a linear operator, you can decompose the vector space into the dark sum of generalized eigenspace, and that recovers Hodge-Tate decomposition. And the eigenvalues up to a sign give you Hodge-Tate weights. In general, it might not be integer. It's called Hodge-Tate sandweights. So in some sense, so once you construct this operator, then you just recover this decomposition. So maybe just one simple example, just a Tate twist. P1, which means that the Galois group XY, the cyclotomic character p-adic cyclotomic speaking, sir. I mean, it factors through. I think right. This and what's the Snell operator here? So this GP cross just you can take it's the algebra action on this QP vector space. Extend it to CP, but actually in this case here, so already acts on this QP1 part. And by the logarithm map, you can identify this the algebra for GP cross naturally with just QP. And in this case, the element 1 just gives you the Snell operator here. So XY. P1. So the point is that in this special case, so you already see that the Snell operator really comes from the Lie algebra of your group. So in some sense, so roughly speaking, this already gives you some hint that actually the action of a Snell operator comes from the Lie algebra of the Galois group. And this is indeed the case. So already the algebra. There's actually another way sort of to see this. Since I mean I didn't quite say just say for each V you can attach such operator. But actually, what's then proved is that actually this construction, this sorry here, it's not an arbitrary operator. It commutes with direct sum and yeah, compatible with the tensor product and taking view. So from the Tanakian point of view, then you should believe that I mean it comes from something here. But actually, you can turn this really into a mathematical statement. So what I will say is that if you, from Tanakian point of view, there exists some universal sum operator. And so here's what's then proved. So I mean the Galois group is very big. I mean you can try to make sense of the algebra, but I will just restrict it to a setup so that there's a naturally defined the algebra of the Galois group. So just restrict myself to a case one. You just have a Galois extension. With Galois group is a finite dimensional p-adic group. And let me call this Galois group G. Oh, sorry, by the way, are there any questions?
Yes, you've described in your example an operator acting linearly on a one-dimensional CP vector space, so it's a scalar. What scalar is it?
One.
It's just one.
Yes.
So in the example of QP take twist n, what would it be?
N.
N. All right, cool.
Any other questions? Oh, okay. Yeah. So what's then proof is that so there is a universal sum operator we can know by theta k in the Lie algebra of this Galois group. So because it's a finite dimensional p-adic group, so you can talk about this Lie algebra. But everything is up to tensor CP, so leaves there in the CP complexify the algebra, and it commutes with the Galois action, so it's also actually in the invariance of the Galois group. So Galois group acts again diagonally here. So here is the joint representation. Here is just the usual action. So this is what you should consider the universal sum operator in the sense that if you have a p-adic Galois representation, so if you have a Galois representation, factoring through this G, so because it's finite dimensional representation, any finite dimensional representation of a p-adic group is locally analytic. So in particular, this Lie algebra acts on it, and I can complexify this representation. And here we have this universal one, and it's universal in the sense that it gives you this sum operator for this particular p-adic representation. So that's why it's called universal. So some few remarks. I want to explain in detail. So first thing is that so it's clear from this formulation that as long as you can take, I mean, for any Galois representation, as long as you can take its Lie algebra action, is sort of already implied that you can define the operator. So in particular, you don't have to restrict yourself to finite dimensional Galois representation. So it can be infinite dimensional, but you need to restrict yourself to the case of a locally analytic representation. You can be infinite dimensional. Locally analytic. Not going to define it here, but regardless, some nice plots of representation where you can take the ultra action. Second is I don't think I will use this later, but still I want to mention that so one nice thing about this operator is that you can use the Sen operator to calculate a Galois homology. So it just turn this kind of HI GQP V tensor CP. This is some Galois homology of so highly non-commutative group into some linear algebra problem.
The condition that this operator commutes with the Galois action is making K Abelian?
Not necessary. It can be arbitrary.
Oh,
Yeah.
it has to be invariant.
Yeah, because the Galois group acts diagonally here, it also acts on CP. Okay. It's not necessarily abelian.
If G is ZP.
I'm going to.
Oh.
No, I'm going to say this case and CP cross, but maybe it's different. Is that what you're going to ask?
Well, I kept thinking if Lee G was like ZP, the Tate twist, and this and bring it this space of invariance would be 0. So I was trying to.
No, there's one. No, in that case, Lee G. Okay, let me just go about that. So just the cyclotomic extension. And the Galois group in this case is ZP crossed by the cyclotomic character. So there's no Tate twist on the Lie algebra. So actually the Galois action, the joint representation is trivial. So in this case, so Lie K tensor CP, if you take the Galois invariance. Thank you. Because they act trivially here, and so you're just taking the invariant CP, which by Tate is just QP. So it's just Lie G, which is again by logarithm, it's just QP. And not surprising, so the one here is just a set of the QP cyclotron.
Louis, just to check, like if I have any 5-dimensional representation of B, there's some G now that works. I mean, the image has to be some G.
Yes, you can take the image of the Galois representation.
So somehow this theory always includes any example, but the G changes from representation to G has to kind of change.
Yeah. So there's some compatibility when you take a larger extension, and yes, certainly there is such. So I was about to say you can take the inverse limit of all such K, and they are compatible, and this one way to really realize this. This is something in the Lie algebra of the Galois. Yeah, after tensor CP, and you have to be careful where to tensor CP. So that's why I don't want to really state it. Yeah, let me just restrict to this form. And the very nice thing about this form is that actually this Sen operator knows a lot about this Galois extension. So I want to mention several results, very nice results of Sen. So even though I can put into one statement, but let me separate them. So first is, so what's happening when the Sen operator is 0? Okay, so I will just restrict it to this setup. K over QP is always a Galois extension with Galois group being a p-adic finite dimensional p-adic group. The same proof that this operator is 0 if and only if this K over QP is potentially unramified extension. So potentially unramified just means that if you look at the Galois group of this extension, and there's an inertia subgroup, and this is a finite. This is finite. So after a finite extension of QP, then this extension becomes a completely unramified extension. Okay, so in particular, so another way to think about this is when G is at least two-dimensional, then it's always it cannot be potentially unramified, and so this operator is never zero. Two is what's happening in the other extreme. So when it's not zero, but in this case, you only have either zero or non-zero. But we will see that in general, so it's corresponding to two extremes. Actually, he proved some very nice thing about the ramification group of this Galois. I would just mention one consequence of this result, but of course there's no language. So this is a perfect way view. Of course, at sense time, there's no such thing. But basically, it implies that. So you see that, so this is a very simple, not simple, this operator knows really a lot about this field K itself. And what I find very surprising is that this, in some sense, this is a very rational story. So if you think about Hodge-Tate decomposition, everything is rational. But you already know something happening on the integral level. I want to say something more, but I feel I might not have enough time. So let me just mention this. So there's another very nice description of Sen operator due to Berger and Pommes. So it's much more recent. So it gives you some kind of differential equation. So if you look at K hat, yeah, sorry, I forgot to say this is the p-adic completion of K. So this p-adic completion is a p-adic Banach space equipped with continuous action of G, and you can look at its locally analytic vectors. So it's of a G locally analytic. And once you pass to the locally analytic vectors, so the Lie algebra of G acts on it. And what Berger and Pommes proof is that the G tensor CP, so we can extend this map CP linearly to an action to CP. So just extend this the algebra action CP linearly. And so what they prove is that actually zeta K annihilates these locally analytic vectors. Okay, so this proves that so it's a subspace of locally analytic vectors. So it's a dense subspace, and it satisfies some first order differential equation. And actually, what they prove is even more. So in some sense, they describe that this this subspace basically, in some sense, is the roughly speaking, all the functions on K that satisfying this differential equation. So it can be made much more precise than that, but I will just say this. Okay, so this is the background on the classical dense series. So now I want to move on to the geometric setup and yeah, talk about some results parallel to this theory. Other questions before doing that?
Yes, any question. So if this group G is arbitrary,
Yeah.
So not necessarily the times or something. So why doesn't it get one more set of operators? Why is there only one, but not like several?
How should I answer your question? So you always at the end you decomplete and get back to this cyclotomic one. You just at the end they all come from this extension.
Okay.
And another way to think about this is like QP is like a curve, and that's why you only get one operator. So we were seeing geometric setup when it's over a d-dimensional variety, then you get d operators. For this sense.
In the cyclotomic case, what is k hat locally analytic? Is it just 0?
No, it's yeah, sir. That's a good question. Thank you. So yeah.
No, it's not different.
It always contains all the smooth ones, so it's just a QP dichotomic itself. Because the Galois action is locally constant, so it's locally analytic. And you see in this case, the cell operator acts at 0 here because well, it's locally constant action, so the ultra action is trivial.
Pardon my ignorance. I thought the center operator was 1.
It's 1 in the Lie ultra. Because you identify the ultra with QP, but then
this action is 0.
yeah, it's actually 0.
This map from V enter CP times this CP.
Oh, it's just you extend this action CP linearly.
Because the action back.
Oh,
So maybe you have a L tensor A in VG tensor CP. Say some V. The pairing is just LV, A times LV.
Have we seen it? Is there an example? Yeah, sorry for the diversion, but have we seen an example where the action is not 0?
Yes, you just take a K not Lue Pan's case. You should start with K. So your base is not QP, and then sorry. Wait, so this is always 0. So now we're going to
The action on locally analytic vectors is always
Yeah.
0.
yeah, but the ultra, the whole ultra, I want to say acts on the local analytic vector is not 0 in that case.
Oh, there's other elements within Lie tensor CP which
Yes.
don't annihilate, right?
Yes.
Yeah, I guess if we take the splitting field for singular.
Yes. Any other question? Okay, so
So just a remark, it might be helpful for people to remember when you're thinking about this, that k hat tensor, like you do the completed your uniform completion with tensor product with CP, but it's just continuous functions from G to CP. So sort of think about how B and G react things inside of that.
you mean this tensor with CP?
Yeah, if you take the like, uniform completion of k hat tensor.
Yeah, you have to be careful with what's
But just so people know that this is really just some form of continuous functions from G to CP.
But I disagree. I feel if you take the tensor product, complete tensor product regarding this as LB space, then it's not. I mean,
But I'm saying k hat tensor. And not the LA, just the k hat, and then you have to take the uniform completion.
yes.
But just to say that these are just some twists in the end. You're acting on sort of locally analytic things in some sort of twisted form of continuous functions from G to CP.
Yes, I'm
Okay, I know, sorry.
Yeah, for me this is more complicated.
Sorry.
But I agree with what you're saying.
That's a very basic question. It's like if there is a structure of a legal on G, is it always unique?
Yes, that's a good question.
It's a topological group, and that determines the length structure.
Yeah.
It's yes. Okay.
I want to say yes, at least in some neighborhood of the identity. You can recover the Lie group structure.
I mean, like for uniform pro P groups, you can do everything algebraically, right?
Yeah, yes. That's why I want to say restricted to a neighborhood of the identity. So some uniform pro P group, you can just recover everything is algebraic.
The answer is yes.
Yes, yes. Well, I want to give you a proof. Okay, if there's no more questions, so let me just move on to geometry setup. So, for me, I already mentioned that so QP you should regard as a curve, or some people regard that as a curve. So you can, but when you move to you don't have to, so QP, now you can replace by some variety over CP. And so some region analytic variety, or maybe smooth. And so this Galois group, Galois representation, well, there's a very, the corresponding notion is you just consider some local system. P-adic for local system. On X, maybe let's say, we use L. Let me just do use V. I don't know. So in my notes, I use V. Maybe at some point I would just. So let me just use V. I hope there's no confusion. Someone is strongly against. I would change it to L. I hope it's okay. And here, so in this sense theory, since work, so in all this Hodge-Tate stuff, you have this. You consider this V tensor CP with the diagonal action of the Galois group. And so here, what you do is you have this local system, and what's corresponding to CP with the Galois semi-linear action of the Galois group is you just consider the structure sheaf on the pro-état side. Oops. So you get a pro-état vector bundle. So I didn't quite explain how sim constructed, but I already mentioned that at the end, so they all construct reduced to this cyclotomic extension. So in some sense, you have your favorite extension of QP or of local field, which is cyclotomic one. But here for X, I mean, there's no such canonical choice. So you have to fix a chart and then talk about some canonical. Sorry, let me write it down. What I was trying to say. So here you have some very canonical extension, but here you don't have that. So as a result, so what you get is not quite the algebra tensor CP, but I want to say that you get the Higgs field, but I just want to maybe finish this. So what you can do here is you can look at the so for this kind of a torus, you have a very canonical cover, Pro-Etat cover, just by extracting all the piece forward roots of the coordinates. And then if you have a map, some nice morphism from X to it, then you can just put back this cover. At least locally, you can try to do it. But then the question, as I already mentioned, it depends on the choice here. So you have to cook up something which doesn't depend on this choice. The compensate, so as I already mentioned, what you get is actually a Higgs field. So let me just stick to the 0. So yeah, I was about to say, so you can repeat that sense construction with this, using this dictionary, but you have to be a little bit careful about how you glue things. So in this case, so I first did this in the one-dimensional case, and then Juan Esteban Rodriguez Camargo, he did the general case. Actually, he did much more than what I'm going to say, but I will make some remark on that. So if you start with some local system, local system. And then let me call W to be the Pro-Etat vector bundle. I wrote there. Then one can define a Higgs field, a canonical Higgs field. On W, i.e., there's a W from W to W tensor differential form, one form on X with some Tate twist. And Higgs field just means that this is Hodge-Tate linear, which corresponding to its operator is CP linear. And here, the Venn product is 0. So you don't have such condition in the Sun operator. I'll take a Sun operator case because at that time you only have one operator, but here you have, if your base is not one-dimensional, then basically it says that the operator you get the commute with each other. And of course, it's functorial in V, and well, I haven't said anything about this. It can be just 0. So just like there, I say it can be used to calculate the Galois cohomology. Here, this can be used to calculate the push forward from Pro-Etat side to the Etat side. So and the push forward can be computed using, so you have a Higgs field, then you can construct a complex from it on the Higgs complex. Yeah, I won't say more about that, but just want to say, otherwise you might think, well, why can't it be 0? It cannot be 0. And some remark here, like here, maybe I'll just erase this backward, is that, so again, so here you don't have to restrict yourself to a finite dimensions, local system. You can just, if you can define some notion of a locally analytic local system, then you can also attach such a Higgs field. First remark. The second remark is that actually you don't even need to start with a local system. So um, so one can define a canonical Higgs field. For general Fourier vector bundles. So it doesn't have to really come from a local system. I mean, it doesn't have to be of this form. And actually, one even introduced some notion of relative locally analytic ON Banach O Hodge-Tate sheaf. So yeah, so that's one maximal generality you can define such thing. So basically, it's like a Cartesian. Like I already said, you can allow V to be infinite dimensional locally analytic, and here you can also allow it to be vector bundled answer if you combine these two notions. And also, I want to, so also there's some very nice feature about this operator. So for example, and this is 0 if and only if this W can be descended to a tau vector bundle. So you should really compare this with the p curvature in characteristic p case, and indeed that actually this is the case. I think that it's a really mathematical statement now. But so as someone who studies scholar representation, I won't go into this direction. So I want to just come back to this and erase that. And I want to say so. Yeah. So in the Blackboard, I just erased this. So Sen has also, this universal Sun operator. You can also define this universal Higgs field. So what's the setup here?
Can I add something?
Yeah.
So in this case, when theta W equals 0, does it say something about original Shelley local system?
I'm going to come back to these two theorems. Yeah, thank you. No theorem. Sorry. So let X theta be some probably talk power. But say the G tensor X. And then yeah, again, so G is the finite dimensional p-adic link. And when you can generalize sense work in this setup and you get the following. So from this, so there's a universal Higgs field, say the X theta, in Li G, and here the tensor CP, as I mentioned, you replace it by a completed structure sheaf, and here is a Higgs field, so you also need to twist by the structure sheaf. Sorry, by the one form. So there exists such a universal one with the property as I already. I mean, you can imagine being a universal one. So another way sort of to think about this is that instead of some elements in the one form space, you can also just regard as a morphism from the tangent space to the Lie ultra. and also there's a generalization of we're doing harmonics work. So and the zeta x theta annihilates the locally analytic locally functions here. So it yeah, you can. And so in some sense, so the locally analytic functions, they satisfy some differential equation, and I always regard this as some kind of p-adic Cauchy-Riemann operator. Some differential operators satisfied by the analytic functions.
In this first line, so here VG is the local system coming from the adjoint representation for X tilde.
Yes. Yeah. I want to make one remark, but if X is defined over so if X is defined moreover over QP or finite extension over QP, so if everything is defined over a discrete, finite extension of QP, then actually you can combine this geometric this Higgs geometric sound operator and the original sound operator in the sense that actually this Higgs field so you can define you can lift this natural map to W tensor the faulting system extension. It's by one this faulting system extension. You know, probably know that it's an extension of the one form by all hat twist by one. So sponsors actually you can try to combine this with the sense form. So I have still 10 more minutes, so I really want to come back to these two results. I want to say what are there any generalizations of these two results? And we do have some result which is very nice, but maybe not as good as what I explained here. First, what do we know about when this Higgs field is zero? This results. I mean, basically, I think it basically follows from Sasha Petrov's paper. So I would really. I mean, all the constructions. I mean, I basically followed. So it's in his paper. So I would like to attribute this to him. I'm not sure if you agree with this. You will see what I'm going to say. So let's say X is defined over some finite extension of QP, and let's say it's proper smooth. And let's say that we have a local system such that the corresponding Higgs field is zero. Then in some sense, so the sense result, so you should regard this as a generalization of that condition, and well, it's also A-time only, but I would just say it's going one direction. They say it's potentially unramified, and so here the result is that basically it's pointwise potentially unramified up to twist by some local system. So then we can be embedded into a tensor product of two local systems, V0 and V1, such that where V0 so pullback along So you have x to of the points. So it's just a constant local system. So we say equipped with a Galois action. So the monodromy action is trivial. Then V1 is a pointwise potentially unramified local system. So i.e., so V1 x just take a point of you on x, and you regard as a representation of the Galois group is a potentially unramified representation of kx bar or kx for one, or once you know for one, and actually is for every point. Sorry, it's connected geometrically. For every x in xk bar.
How much important is this proper assumption?
At least the argument, if it's not proper, then probably I need to, there's some compactification with simple normal crossing divisors.
Okay, but there is also a local version.
It is a global result.
Okay, no, no.
Yeah, it uses comparison. So I'll just so it's easy to see that actually if you have a vector bundle, have a local system which is a tensor product of these two local systems, so for V0 is just put back from a point. Of course, there's no Higgs field, and the second one basically you can show that after means finite after a finite cover it becomes there's I mean the action is trivial. I mean you can show that's actually the Higgs field has to be zero because the Higgs field involves some Tate twist there. But basically, this shows that all the Hodge-Tate weights pointwise at zero, so it has to be zero. And so this is some kind of converse result saying that if your local system has no Higgs field zero, then it has to be a sub-local system. So so in Sartor's paper, he basically proved that for any local system, you can construct such embedding, and if you're careful enough, you realize that this condition really shows that what I wrote here for V1. So this basically answers. I hope answers Hao-Yang's question. There are questions about this result.
So what you said is the pointwise. So is it possible that, but what you just said, it's possible to have some kind of cover so that after the cover, everything is harmonified?
Yeah, yes, you can.
Oh, okay, that's stronger than.
No, yeah, there's a trick to show that these two actually are equivalent.
Okay.
Any other questions? And what about the second one? Well, there you just require it to be non-zero, but here because in general, if your base has dimension d, and so it's, I mean, simply being non-zero is not a very, I don't know, it's not a correct generalization. So what you can hope is that it's in some sense non-degenerate. So there's a very nice result recent preprint of Tongmu He, saying that actually, so let me state his results. Projective smooth over again. So I think he just works in the algebraic setup. So it can be, if not a projective, but then you need some log version. So I will just restrict to a projective case. And you have some pro-G tensor. So in that case, and assume that so here one way to formulate that is saying this morphism is actually non-zero. One way sort of to think about this is that you just want to say all the tangent vectors if you take a basis, then they are still linearly independent in each.
But tell me what the point is that the dual is rejected. She's a little bit stronger than the thing.
The dual, he
Like
needs
the one that the
This is
intersection.
this has to be injective at every geometric point.
Yes, exactly.
Well, this should be injective at every geometric point, like not just like injective.
you mean it's stronger than being yeah. I was about to say that. Thank you. Yeah. It's a geometric point of x tilde. Then x tilde is he called the say clockwise 3 differentially. Which implies that the residue field x tilde are pre-perfect.
I think that you don't need projective for that.
You don't need this, but then I thought you need some assumption on this for compactification.
I think this is just a condition on the. It's not just a condition on the field.
Let me just restrict to the projective case. Okay. For simplicity. Yeah, you might be right. So this, for example, this so this has some very nice consequence about if you try to study the cohomology of x tilde. So corollary is that if you look at the base change to CP and then look at this état homology, or état homology, let's say just have it just vanishes above middle degree. I mean, so for example, the example is you can take x to be some Shimura variety, any Shimura variety actually, and x tilde to be let's say some Shimura variety with some level, and just the infinite level one level at p. And so you can calculate this semimorphism or the using variety of Hodge structure, and actually it's a dark summon. In this case, so I can say more about actually what is this map, sir. But I don't have time, so actually you can really describe it using Hodge-Tate period map. This is a dark summon. So then, so from this, he showed that if you apply all these results, and then the completed homology above the middle degree vanishes, which was conjectured by Carberry and Emert. completed cohomology. Let me add the following question. So I strongly believe that actually it should be possible to prove. It should be true that actually it's not just a stopwise is perfectly. X theta should be perfectly. If this is true, for example, this reproof shows us result that, for example, for a Hodge-Tate Shimura variety, the infinite level is perfectoid. And even stronger, you don't have to restrict yourself to a Galois, to a Galois, to a G tosser, but just some pro-Ital cover. And this should also reprove that the anti-canonical locus is already perfectoid on anti-canonical locus. So yeah, it'd be very nice if someone prove this or disprove this. Yes, thank you for your attention to this topic.
So, other question?
Yeah.
So, what is the stopwise perfectoid enough for this dimension?
It's very key speaker. I think.
So you don't need perfectoid.
Yeah, I think pointwise is enough to deduce some when you try to push forward from pro-Ital side to Ital side, and this pointwise is enough to get the vanishing for a higher direct image, and then on the topological space is the dimension of X. Like that.
Right, so was this result known before for a certain class of Shimura varieties?
Yeah, Peter. Yeah,
Right.
right. So you proved it.
But now the point is, the new bit is that this works for all the Shimura varieties.
Yes. Yeah, I mean the old proof goes like first proving X theta is perfectoid, or is some compactified version is perfectoid, and then that would be enough. And here Tomu's result saying that well, we don't know it's perfectoid, but pointwise perfectoid is enough to deduce such vanishing.
I guess one had some intermediate result too that wasn't.
Oh,
It was like use less than like something that used less than perfectoid. But
I think one proved that. Yeah, sorry, I should mention that. One already proved that this is torsion before. Yeah. So using this, using. Wait, did I already erase? I mean, using you can calculate an operator. Sorry, you can calculate the push forward from pro-Ital side to Ital side using this heat field. I mean, you already can prove some vanishing results rationally.
I have a question. So with this theorem of Petrov, can't you prove the same thing for X and affinoid?
What? Which one?
Theorem of Petrov.
This is a global result.
It's not true or an affinoid.
What's your theory?
I just follow his proof, but it certainly use proper in it.
The second part is not in this paper, is it? The second part.
No. So yeah, I did this part. But this construction is in his paper differently. Yes. Yeah, it uses a comparison, a primitive comparison. So that's why it requires proper assumption.
And just to make sure, this local system has to have some lattice inside, right?
Yes.
I think it's yes. Everything I talk about a color local system.
Okay, so if there are no more questions, let's thank the speaker again.